Oh, hi guys. Let me just pull this up right here. So this is the last one for the semester in the quantum mechanics, and I really enjoyed this one. I enjoyed the last one too, about Fermi's golden rule, but I really liked the no clone theorem. The no clone theorem was a little unexpected for me. I kind of got the sense right away. I mean, as we're looking at this, I mean, how are you really going to clone things identically when you're talking about spin, angular momentum, and you're talking about energy, and you're talking about position, and you're talking about the Heisenberg uncertainty principle. So I could kind of like feed into why, there is a no clone theorem. But it was a little unexpected in the end when we go through this. So let's go ahead and talk about this here. So, I mean, we generally know that quantum measurements are typically destructive. That when we go to measure something, we collapse the wave function and, we only have one state, instead of two possible states that we could have, through something called the quantum entanglement. You know, so basically, if we took, for example, a positron and electron, um, we may not know their initial states, what they're in, but we can assume that they're in close proximity to each other and that they share the same wave state. And when they do, that becomes a quantum entanglement. And that quantum entanglement basically would mean that there's three possible states for the positron and the electron. That they're going to have a state which is where they have spin up. And they're going to have a state where they're spin down, and they're going to have a state where they're both at the same time. Spin up and spin down, and that's going to be the superposition. And we know generally if we collapse the wave function, then we're only going to see two of those states, which is going to be the up and down state. Now, what we want to do is we want to consider here, go back to Schrodinger's cat, okay, and talk about him in terms of that quantum cat that I mentioned earlier. Um, so that there is a quantum entanglement that between the atom decaying, the atoms decaying, and the cat's state, which is alive or dead. Um, so basically, here, when we start thinking in terms of Schrodinger's cat, if we want to clone that cat, we're really going to be in that mixed state initially. We're not going to know exactly whether that cat is dead or alive or whether it's between dead and alive. So, because we know that Schrodinger's cat can exist in three states, just like the electron and the positron. Okay, so when we come down here, though, we kind of can see the three states. So we have the live cat, the dead cat, or the in-between cat. That's both, that a percentage of the cat is alive and a percentage of the cat is dead. And so we also have here, as you can see, this are kind of our machine here, in which we're going to try to take a cat in a state that we may not know, and we're going to take what's called a blank state, and we're going to take the cat in the blank state, and we're going to put them into our quantum copy machine, and what we're going to do is we're going to get out what the cat, how the cat duplicated, basically. So we're going to get out the original cat, and that blank state cartridge that we're putting in there will then turn into, and if this works, if the quantum copy machine works, into, like, for example, if the initial state was a live cat, then we wouldn't know that, but we would know through the final state by peeking in, right, to that box, that we now have a live cat out, and therefore we expect that our blank is also going to be a live cat. Okay, so we can come here and you can see that's exactly what we get. So from cloning machine's perspective, if the cat was in a live state when it was cloned, we would get out 2 live cats. And you can see the 2 live cats that are right here, taken out of their boxes. Okay, so that leads us to this equation here. And this equation really says that we have, this state 1, and we have that blank state. And what we're doing is, as we put it through our quantum copier, we're getting out that state 1, 2 of them, one for the blank state X and one for the original state of, in this case, the cat. So what we're getting out in this particular case, as you can see, 2 live cats. So that would mean that if I think about it here, I'd have a live cat for the initial state, and the blank state, that'd be the X. And what I'm getting out is a live cat and a live cat. Now, when the initial state is a dead cat, the quantum copy machine also works. Okay, so we're kind of getting here, as you can see, unfortunately, 2 dead cats. Okay, so, and that really works the same way here. So if we are looking at this equation here, we're getting out the dead cat, the blank state, that's the X, and now we've got the dead cat and the dead cat. But what if the initial state wasn't alive or dead, but that we were in a superposition, that the cat was between alive and dead? Then you kind of know what we should get out. If it's going to be a good copy machine, it means that we should really be getting out a cat, the initial cat, which might be in the live state, and then the blank cartridge that we sent through would be in the dead state. And that's kind of what we would expect, but it actually turns out that it's not what we really get. And we can look at this equation here, and this equation tells us that no, we're definitely not going to get that. What we're going to do is, when we put in that cat that's between alive and dead in the superposition, that we're going to get out, as you can see here, you're going to get out either 2 live cats or 2 dead cats, but you're not going to get out an alive and a dead cat. So this gives us 2 possibilities for the initial and blank state, 2 dead cats or 2 live cats, and that's it. This, and again, stating here, I mean, we can read this through. This is not what we would expect from our cloning machine. Since the initial cat is both dead and alive at the same time, we would expect a dead and a live cat, or vice versa. Therefore, our cloning machine works well in orthogonal cases, where your initial state is alive or your initial state is dead, but not diagonals, which means that you're going to be between an alive and a dead state. Okay, so if we kind of come in here now and we look here, we can see that alive and dead are okay, because that's going to be your orthogonal states, but you're not going to be able to, this is the only time the cloning machine will work. So the known clone theory has opened up, so the known clone theory by this has opened up a field which we call quantum cryptography. So quantum cryptography is really good, because if you're only allowed these orthogonal states where you're only going to be alive or dead, then the bottom line here is that quantum cryptography is through sending messages through photons. And what they can do is they can polarize these photons so they're not just orthogonal. And then they can send these messages, and when they send these messages, they're not going to be able to be copied. So you're not going to be able to no one's going to be able to eavesdrop on the message. And then when the person receives it, then the person can translate that message, because they'll have a way of doing that, being told by the person who sent it. But the reality is that this is a whole field that's coming out because of the no clone theory. Guys, this is the last one, but I kind of really enjoyed dealing with the no clone theory, and I don't so much like dealing with dead cats and alive cats, but I've always had little hangups on Schrodinger's equation, and and then seeing it here with the no clone theory and how it can be put together here, it really clears a lot up. So I hope you guys enjoyed it, and thanks so much now, and that's it.